Yes?
How heavy was Odin, and how much did the Russians charge you to launch it?
How heavy was Odin? You saw the size of it. I think, I'm trying to remember if it was less than a metric ton. They charged us $90 million. I don't remember the weight. I probably had it given away at some time. But it wasn't that big. If you don't include the solar shield, it's this size. It's this. But it's all solid copper, right? It's all electronics.
So it's 90,000 kilos to L2.
It didn't go to L2. That was in close Earth orbit, right? 90-minute orbit. We launched right over North Pole, over Washington, in a 90-minute orbit. Yes.
You were saying that one of the biggest problems is the fact that all the components have to withstand such huge vibrations.
Yeah.
Would it be at all possible to move the manufacturing to the International Space Station, or is that not at all feasible?
It seems to me that would be more expensive.
Yeah. But it would
Also, it's a really dirty environment. It's one of the we keep being asked to do science things there. There's many opportunities to do science at the space station, and it's dirty in just volatiles. It's dirty in vibration. It's dirty in radio noise. It's just an environment we don't want to be in. So there was a proposal to try and build one of these large telescopes attached to the space station. That was a European proposal a couple of years ago, and it came from people at the European Space Agency, and all the scientists looked at carefully at it and said, this isn't going to work. You just can't. It's amazing how much things like vibration really, really matter. A lot of these detectors, we don't think they're vibration dependent, but they turn out to be really, really affected by a little vibration. And vibration you've never noticed. I noticed once I was observing at the JCNT, I think with Scuba, the original camera we had, and I noticed that it got really noisy on the signal. The signal I was getting coming in was all of a sudden just went completely to nothing, which is really awful. And I couldn't figure out why. And eventually we decided we were going to have to go out with the dome. We're sitting in a control room looking through some glass windows out where the dome is. And so we eventually decided to go out and see if there was something wrong with the instrument itself. We went out and there was loudspeakers, and I had turned up the loft a little too loud indoors and not knowing that the outdoor speakers were on, and the sound from that was upsetting the instrument. It didn't like rock and roll. Loud. Just a vibration. Microphones. Yes?
Curious, you said one of your satellites, so you put it in a very unstable position to avoid all the dust that collects.
That's right, yeah, the L2 point. That's where everybody's sending their stuff these days.
So what do you do about fuel? Do you have to keep restabilizing, or just
well, it doesn't take very much fuel. Most of the motion is done with gyroscopes. There's not very much that requires you to use fuel. Fuel is just used really for changing the orbit, and the orbit's pretty stable. For pointing, you're just using electric motors on gyroscopes, you have 6 gyroscopes. You have 3 redundant in three directions, and you just rotate the satellite. It's a standard problem I use in Physics 115. I use it as an example when I teach Physics 115 as moving a satellite, and as a gyroscope you speed up and things like that. You get the satellite to rotate and how long it takes and things like that. So you don't use a lot of fuel. You just use electricity, which is free. You have solar panels. Yes?
You mentioned that with Herschel, a lot of things seem to be coming out warmer than you expected.
Yeah. So the main object I'm working on right now was it's a place where there's a cloud forming a star, a couple times more massive than the sun, and I had modeled this. In fact, this now the instrument stuff's done. I'm responsible for modeling and doing all this radio transfer code and photons stuff in the computer. And I had modeled this thing, and I predicted that the inner edge would be maybe about 300 degrees, and the outer edge is about 10 degrees above absolute zero. And then I predict from that lines I should see, this particular line of carbon monoxide and this water line and things like this. And you can look at those lines, and if it's really hot, there's some very high excitation lines you'll see. Well, we've seen all these high excitation lines, some with excitation temperatures of 1,500 degrees, completely incompatible with my model, which is kind of sad. But all these Europeans are, I was on a teleconference yesterday for 2 hours of people discussing shocks. We'll have to add in shocks, which is a completely new range. It's like a 3-year job to write a good numerical code to predict these things. And I don't want to do 3 years for a paper I want to produce in the next 2 or 3 months. And it's an intense we're really intensively trying to produce this data, trying to understand the data that we got out because it's not explaining the current models. So we were trying to think yesterday, what current existing code can we adapt quickly to try and reproduce the observations. And it's challenging, but it makes it also very exciting, and you also lose a lot of sleep. I've been pulling all these all-nighters. I'm not used to doing this.